We are going to finish the first part of Unit 1 looking at density. And density is the amount of mass in a certain given amount of volume. So this is a physical property. We'll get into what physical properties are more in the second part of Unit 1, but these are characteristics. These are things that are unique to individual substances, and it's how you can tell different metals or nonmetals apart from each other. They all have a different density. It also tells us how closely packed the particles are. So if you take a look at this example, volume of these two particles are the same. Styrofoam and the brick have the same volume, length, width, and height. But if you look at what they're made up of, the styrofoam, the particles are really far apart, so there's a lot of empty space where the mass, you'd have a lot of air, which weighs less, has less mass. Whereas the brick, the particles are very tightly packed together, held together much more closely, and so the brick has a higher mass compared to the volume, so the density is greater. Whereas the styrofoam has a smaller mass compared to the volume, and so the density is smaller. Again, we notice that they're the same size, but the material in the brick is packed closer together, which makes the mass more. Even though the volumes are the same, they have different densities because the masses are going to be different. So there is a way for us to calculate density, and density is going to be mass over volume. So we're going to take the mass of our object, divide it by the volume of our object. And if you look at the practice problem that already popped up, let's say we have a book with a mass of 500 grams and a volume of 1,000 centimeters cubed, and you were asked to calculate the density. We could use this equation, and we will plug our numbers in. The mass, 500 grams, goes on top, so we have 500 grams here. And the volume is the 100 centimeters cubed. And we know the centimeters cubed is volume because that would be length times width times height of a solid object. Now when you divide 500 divided by 1,000, we get 0.5. And notice each one of these has one significant digit, so we're only allowed one significant digit in our answer. And every quantitative measurement needs a number and a unit. So we have grams, we also have centimeters cubed. Neither of these can cancel or go away, so we have grams and centimeters cubed in our final answer. Let's take a look at this example. We have a substance, we don't know what it is, but we know the volume is 4 centimeters cubed and the mass is 3.2, and you're asked to calculate the density. So again, we can use our density equation. Density is mass over volume, and we know our mass is 3.2 grams. We know our volume is 4 centimeters cubed. You need to be thinking about significant digits as you do this as well. When you calculate out your answer, we get 0.8. We know that we're only allowed one significant digit because the 4 only has one, and it's the lowest amount. Notice our units cannot cancel, so this object, whatever it is, has a density of 0.8 grams for every 1 centimeter cubed. 0.8 grams per centimeter cubed would be the density. For this one, we already know the density, and you're asked to come up with the volume. What would the volume be of this object? We know the mass and we know the density, and so we could calculate this one of two ways. And I want to show you both ways so that you can use whichever one you would be most comfortable with. We can do this the same way we just did the previous problem. Plug and chug is the way my math teachers used to give us equations. You plug in the numbers and then you chug out an answer with your calculator. We know the density is 0.2 grams per centimeter cubed, and that is equal to the mass, 0.4 grams, only now our unknown is the volume. That's where I'm going to put my x. So to calculate for x, to calculate for my volume, I want to cross multiply. So I have 0.2 grams per centimeter cubed times my x, and that's equal to 0.4 grams. And then to get x by itself, I divide by the 0.2 grams per centimeters cubed, And that will all cancel and go away, so I'm left with x. And x is going to equal 0.4 divided by 0.2, which is 2. And my grams are going to cancel. I'm going to be left with centimeters cubed. And remember, you were looking for a volume, so it makes sense that centimeters cubed should be the only unit you have left. Now, in my opinion, that is a lot of extra work. Here is another way that you could set that up. I know some of you just love dimensional analysis and showing all of your units, but let's say that we have 0.4 grams, and we know because of our conversion factor, density is actually a conversion factor, 0.2 grams for every 1 centimeter cubed. And you could do this dimensional analysis wise, cross out your grams because they will go away, and if you take 0.4 times 1, you get 0.4, divide that by 0.2, we get 2, and you're left with centimeters cubed. You could do this either way, you'll get the same answer either way. In my opinion, the dimensional analysis has less work involved. Now, lastly, we need to look at how we evaluate our measurements. You hear people say, oh, that was really accurate or that was really precise. We need to know what that means. Accuracy is how close your measurement comes to the actual true value. So let's say that we know, for example, that our table is exactly 100.0 centimeters across, and we know that for a fact. And some other student comes along and they measure it and they get 76. Well, their number was not close to the true value. They were pretty far off. So we would say that number is not very accurate. Okay, so accuracy deals with how close it is to the exact measurement. Now, precision refers to how close the values are to one another. So let's say a few more students come in and they measure. We have the first one that gets 76, another student gets 75, and another student gets maybe 76.5. Well, those numbers are all pretty close together. And so those three numbers we say are precise because of how close the values are to one another, but none of those numbers are accurate, meaning that they're still really far away from the true value. You have a picture that kind of shows accuracy and precision. In this target, accuracy is hitting the bullseye. If you hit the bullseye, then you were very accurate. So in this picture, notice it hit the bullseye, so we're accurate. Notice the grouping of the arrows, they're all really close together. Precision deals with how close the values are to one another. So in this, because the arrows are really close together or grouped together, we would say it's accurate because it hit the bullseye, it's precise because the arrows are close together. In this example, it's accurate because we hit really close, right on the edge there of our bullseye, but our arrows are not really grouped together. They're kind of spaced further apart, so they're not precise. Here we have an example of precision. Notice the grouping, they're all really close, but yet none of them hit our bullseye, so none of them are accurate. And then in our last example, again, the grouping, we have them really far apart, so they're not precise, and none of them hit the bullseye. So these arrows are not accurate, and they're not precise.